Hi, welcome to my class in Mathematics in the Modern World. This mathematics course, Mathematics in the Modern World, replaced the mathematics courses in the old general education courses for college students. In the old general education courses for college students, the mathematics courses that were replaced by Mathematics in the Modern World included algebra, plane trigonometry, business mathematics. These courses were taken out from the general education courses for college students and they were brought down to senior high school. This mathematics course, the Mathematics in the Modern World, is required for all college students regardless of their program. For our first lesson for today, we will take up linear programming. For understanding better mathematics in the modern world, you should have at least some background of algebra. We now proceed to our first lesson, Lesson 1 on linear programming. Linear programming is a quantitative technique or it's a quantitative tool used for optimal allocation of limited resources. The given in a linear programming problem are resources, but these resources come in limited supply. And we are seeking the best allocation of these limited resources in such a way that we meet the objective in our problem. The objective in a linear programming problem can either be to maximize or to minimize. In linear programming problem, there can be more than one solution. In fact, we will have problems that will have infinitely many solutions. And among these infinitely many possible solutions, we want to select the best solution, thus the optimal solution. It's the solution that either maximizes our objective or that minimizes our objective. An example of a problem that we will solve in linear programming is this linear program. This set of linear function and linear inequalities make up what is known as linear program. A linear program is the mathematical translation of a problem. The problems that are solved in linear programming are based from real-life problems. But for mathematicians to manipulate the variables, they translate these real-life problems into a set of equations, inequalities, and functions. And they call this mathematical model. In a mathematical model, there are assumptions and conditions that are given. If one of these assumptions or one of these conditions changes, then the mathematical model has to be revised. In linear programming, the mathematical model is known as linear program. Again, a linear program is the mathematical translation of a real-life problem. And this is an example of a linear program. A linear program has actually three components. The first component is the objective function. In this example of linear program, the objective function is given by this function. Our objective in this linear program is to maximize z. We want to find the maximum value of z, and z is a function of two variables a, and b. Our objective in this linear program is to find those values of A and B that will give the maximum value of C. The variables A and B are known as decision variables. They are called decision variables because at the end of the solution, we will decide on the values of A and B among the many possible values for A and B. We want to select the values for A and B that will give the maximum value of C. But we maximize the value of C subject to, ST stands for subject to. We maximize the value of C subject to the following constraints. Again, in a linear program, we have three components. The first component is known as the objective function. The objective function can either be to maximize or to minimize. In this example of linear program, the objective is to maximize C. Our objective is to find the values of the decision variables A and B that will give the maximum value of C. But we do that subject to the following constraints. These four constraints are grouped into two groups. The first two constraints are known as explicit constraints. Explicit constraints. And the last two constraints are known as implicit constraints. Implicit or implicit constraints. Again, the linear program consists of objective function, and we find the values of the decision variables that maximizes Z subject to the following constraints. The constraints are grouped into two. The first group is known as explicit constraints. The second group is known as the set of implicit constraints. The explicit constraints are constraints on the availability of resources. In a linear programming problem, these explicit constraints are given. For instance, if your problem is about production, in a production there are resources, and these resources come in limited supply. So these resources impose limitations on the values of the variables or decision variables. Or we say these resources impose constraints on the values of the decision variables. But in a production problem, we require all the decision variables to have values that are positive or zero. Because in a production problem, negative values for the variables will have no real significance. And these constraints that require the variables to have positive or zero values are known as the implicit constraints. The implicit constraints require the variables to have values that are either zero or positive greater than zero. Again, the implicit constraints require the variables to have positive or zero values, and they are also known as non-negativity constraints. In linear programming, our objective is either to maximize or to minimize. And a problem that is solved by a method for linear programming problem is given in a linear program. A linear program is the mathematical translation of a real-life problem. The real-life problem is translated into a set of equations, inequalities, and function. And in linear programming, we call this set of equations, inequalities, and function as linear program. And this is an example of linear program that has three parts. The first part is the objective function. The objective function specifies whether your goal is to maximize or to minimize. The first component of linear program is the objective function. The objective function specifies whether your goal is to maximize or to minimize. In the objective function, you will see the decision variables. In this example, the decision variables are A and B. And we are looking for the values of A and B that will give the maximum value of C. But again, we do that subject to the following constraints. The second component of linear program consists of the explicit constraints. Again, the explicit constraints are constraints on the availability of resources. And the third component of linear program is known as the set of implicit constraints. And these constraints require the variables to have values that are positive, greater than 0, or 0. So in linear programming, the values of the decision variables can either be positive or 0. So these implicit constraints are also known as non-negativity constraints. Notice in the objective function, the exponent of the decision variable A is 1. The exponent of the decision variable B is 1. And this function, Z, is a function of A and B. And the exponent of C is 1. Because the exponent of each variable in this function is 1, this function is known as linear function. In the explicit constraints, you can see that the exponent of A is 1. The exponent of the decision variable B is 1. And we have the less than sign in this constraint. So this explicit constraint is known as linear inequality. It is called linear inequality because the exponents of both the decision variables A and B are 1. And it is an inequality because it contains the less than sign, one of the inequality signs. Similarly, in the second explicit constraint, the exponents of A and B are 1. So this explicit constraint is also a linear inequality. It is a linear inequality because the exponents of A and B are 1, and it contains one of the inequality signs. In particular, it contains the less than sign. The same with the implicit constraints. The exponent of the decision variable A is 1. The exponent of the decision variable B is 1. So the exponents of every variable from the objective function to explicit constraints to implicit constraints, the exponent of every variable is 1. This is a linear function. these are linear inequalities because the linear program consists of linear function and linear inequalities. This topic is known as linear programming. Linear programming because all the equations, functions, and inequalities involved in a linear program are linear equations, linear function, or linear inequality. There are two methods for solving a linear programming problem. But before we go to those two methods, let us summarize what we have discussed so far. Linear programming is a quantitative technique, or it is a quantitative tool that is used for optimal allocation of limited resources. The problems that we will solve in linear programming are based from real-life problems that are translated into what is known as linear program. A linear program then is the mathematical translation of a real-life problem. And a linear program has three components. The first component is known as the objective function. In linear programming, our objective is either to maximize or to minimize. But we do that subject to a set of constraints. And the second component of linear program is known as the explicit constraints. The explicit constraints are constraints on the availability of limited resources. And the third component of linear program is known as the implicit constraints or non-negativity constraints. They require the decision variables to have values that are positive or zero. That's why they are known as the non-negativity constraints, which means that in linear programming, we will not have values that are negative for the decision variables. Now, the two methods for solving linear programming problems are: number one, graphical method. The second method is known as the simplex method. We will use both of these methods to solve our example of linear program, the linear program we had earlier. And we will solve it by using first the graphical method, and we will solve it again using the simplex method. And using both methods, we should get the same answer. But the graphical method has a limitation. The graphical method can be used only when your linear program involves two decision variables. Although we can graph in three-dimensional space, it will be extremely difficult to do that for three decision variables. So the graphical method is used only for solving a linear program that has at most two decision variables. On the other hand, the simplex method is a generalized technique for solving linear programming problem, which means that the simplex method can be used to solve a linear program with any number of decision variables, even with 100 decision variables. There is actually a program for solving a linear program that involves many decision variables. Again, the two methods for solving a linear programming problem are: number one, the graphical method, which has a limitation. It can be used only for a linear program with at most two decision variables. The second method is known as the simplex method, which is a generalized technique for solving linear programming problem. It can be used to solve a linear program with many decision variables, with more than two decision variables. The simplex method was developed by a German mathematician, and his name was George B. Danzig. George B. Danzig developed the simplex method, the generalized technique for solving linear programming problem. It can be used to solve a linear program with more than two decision variables. But the graphical method can be used only for linear program with two decision variables. Again, the two methods for solving a linear programming problem are 1. The graphical method, and 2. The simplex method. The graphical method has a limitation. It can be used only to solve a linear program with at most two decision variables. But the simplex method can be used to solve a linear program with any number of variables, because the simplex method is a generalized technique for solving linear programming problem. The simplex method was developed by German mathematician George B. Danzig. I mentioned to you earlier that when mathematicians build their mathematical models, they make certain assumptions. And the mathematical model holds true only under these assumptions or under certain specific conditions. One assumption in linear programming is known as the divisibility assumption. Again, the divisibility assumption is an assumption made for linear mathematical modeling in linear programming. For instance, in a production problem of tables and chairs, at the end of production we expect to produce, say, 10 tables and 25 chairs. These numbers 10 and 25 are known as integral values, which means that the numbers 10 and 25 are integers. However, in linear programming problems, when we actually solve a linear program, you will find that at the end of the solution, the decision variables will have non-integral values, which means that the values of the decision variables are sometimes not all integers. Some of the values of the decision variables can be decimal numbers or fractions. Those numbers, fractions, or decimal numbers are non-integral values. But in linear programming, we accept those non-integral values or decimal numbers for the values of the decision variables. And that is what is meant by the divisibility assumption. Although we cannot actually produce, say, 9.75 chairs or 25.1 tables, we accept those values, non-integral values, for the decision variables. And that is known as the divisibility assumption in linear programming. In our lesson 2, we will take up the graphical method, and we will solve the linear program we had earlier using the graphical method. If you are so interested about programming, there are other types of programming, including goal programming, integer programming, dynamic programming, and non-integer programming. And you can search for these other types of programming in the internet. If you have questions about the lesson today, you ask your questions in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalisan. Thank you.